Hello everyone, I'm Deepak from MIT and I'll present to you our paper FarmBeats, which is an IoT system for data-driven agriculture. This is joint work that was done at Microsoft with Zerina, who's actually here, Jongho from Purdue, Xinxin from UCSD, Ranveer, Ashish, Sudipta, and Madhu from Microsoft Research, and Sean, who's a farmer who's helped us with this paper. By 2050, the population of the world is going to be 9 billion. To feed all these people and to make sure no one goes hungry, we need to double the amount of food that we produce today. While we need double the food, the resources that we have to produce that food are shrinking. Water tables are going down all across the planet. The amount of land that is fit for agriculture is shrinking because cities and towns are expanding and taking up that space. And while we do that, we need to be conscious about the environment as well. Farming has been one of the biggest contributors of greenhouse gases to the environment. So we need to be conscious of the environment while we achieve that growth. In fact, one of the most worrying statistics that I've seen of late is this. This graph plots the number of hungry people on the planet from 1970s to 2010. So when the first green revolution happened in 1970s, we had more food, and the number of hungry people on the planet started going down. But of late, that growth has stagnated. So what we actually want is the second agricultural revolution. And thankfully for us, agricultural researchers have figured out a solution for us, data-driven agriculture. Let me tell you what it means. So a traditional farmer would typically treat his entire farm as one single unit. So if I want to irrigate this field, what I would do is take some finite amount of water and apply it uniformly all across it. So the data-driven agriculture paradigm says that this is not the right way to go about it. Instead, what you should be doing is to measure the amount of moisture in each part of your field and then treat it accordingly. And you can think of doing something similar for different kinds of farm inputs. You can do it for fertilizers, manures, nitrogen, etc. So this concept has been around for around 2 decades, and researchers have shown that it can lead to tremendous benefits for the farmer. It can reduce the amount of waste, it can increase productivity for the farmer and the profitability, and it can ensure sustainability for the environment. So this is great. I told you about a problem that we don't have enough food, and then I presented to you a solution. We should be doing that, right? What's missing? Well, the problem is that farmers are not using data-driven agriculture because of the high cost of manual data collection. If I'm a farmer today and I want to use this data-driven agriculture paradigm, I have to take a sensor with me, put it in the soil, measure that value. And then I have to walk a few steps and do it again. And I have to keep doing it for my entire field, which can stretch miles. Clearly, this does not scale. But let's look at this problem again. The problem is manual data collection. We're networking researchers. We solve these problems every day, right? We take a manual data collection process and make it automatic. So let's try doing that. So let's try building an IoT system for agriculture. And let's start with something really, really simple. We take these sensors and spread them all across the field. And then we connect them to the internet using cellular connectivity. And then we send all this data to the cloud. This should work, right? Like all of our IoT systems today are built like that. My Nest camera takes my pictures, sends it to the cloud. My Google Home, Amazon Alexa, all of them work on a similar principle. This should work for the farm. Unfortunately, it does not. And let me tell you why. Farms do not have any internet connectivity. Most farms in the United States don't have any internet connection at all. These farms are in rural areas which are sparsely populated and don't have cellular coverage. And even if they have some connectivity, this connectivity is prone to weather-related outages. There can be a thunderstorm and your network might be down for weeks. And not just that, they don't have any power sources. So the way I think of an IoT sensor today is I take a sensor, plug it into my wall, it measures something for my home. Unfortunately, you can't do that for a farm, right? Like there's no power sources on the farm. But what you can do is to rely on other sources like solar power. But there's a lot of variability in solar power depending on the weather. There can be a few cloudy days and your system would go down. And finally, you want to be able to work with a sparse deployment of sensors. So in an ideal world, you would want to place a sensor at every square meter on the farm, get as much information as you can about the farm, and get a fine-grained map of your field. But unfortunately, that's not practical. A farmer has to navigate around these sensors, animals walk on these fields. You cannot deploy a sensor at every square meter. In general, it's also very expensive to deploy and maintain all these sensors. And these constraints are not just specific to agriculture. They occur in various different scenarios. You can think of mining, oil fields. They have the same constraints. They have no internet connectivity, no power availability, and you have to work with a small number of sensors. So the key question that I want to ask today is how can we design an IoT system in challenging resource-constrained environments like these? And that's exactly what I'm going to talk about today. I'll talk to you about our system FarmBeats, which is an end-to-end IoT system that enables seamless data collection for agriculture. It can take data from all those kind of sensors that you can imagine, sensors, drones, cameras, digest that data, and provide services to the farmer. The farmer can then access the services at his cell phone or his computer. Of course, to do that, I need to solve the three challenges that I told you about. We have built FarmBeats and we have deployed it in two different farms. One is in upstate New York and the other one is in Washington State. And these deployments have run for 6 months, and I'll talk to you about our deployments towards the end of my talk. So let's start with the first question. How can we build an IoT system when we do not have internet connectivity on the farm? Before we do that, let's take a step back and try and understand what we have on the farm. So there is the cloud that we want to connect to. And then there is some internet connection at farmer's home or office, which we can use. And on the other hand, we have these sensors, which we want to connect to the internet. These sensors are on the farm, which is typically a few miles away from the farmer's home or office. And this space in between farmer's home and office and the sensors is filled by a lot of crops, tree covers, canopies, really hard to go through. So how can we extend the connectivity that exists at this farmer's home to these sensors in spite of all these obstructions? Our idea is to use TV white spaces. TV white spaces are unused part of the TV spectrum, and researchers have recently shown that you can use them to provide Wi-Fi-like connectivity. So our insight was that we can use these TV white spaces to enable connectivity for sensors on the farm. And that works great for us for 3 reasons. One, they can provide long-range connectivity. TV white spaces work over long ranges like 10 miles. Since they operate at lower frequencies, they can travel through crops, canopies, and forests. And finally, since these farms are in rural areas, there's large chunks of free TV spectrum available. So you can utilize all of that to provide high bandwidth connectivity for the farm. So you can now operate drones, cameras, any kinds of sensors that you would want. So what we do is to take these TV white spaces and establish an IoT base station on the farm that can talk over these white spaces to farmer's home or office. And this base station now acts like your Wi-Fi router. You can connect these sensors to this over Wi-Fi, Bluetooth, or any other technology that you would want. Okay, so this solves one part of the problem. We brought this connectivity from farmer's home and took it to the sensors. Are we done? Can we just ship all this data to the cloud? The sensors are generating a lot of data. Can we just ship it to the cloud? Not really. Remember, this farm is in a rural area where the connectivity is really weak, the bandwidths are low, and even this low bandwidth connection is being shared by multiple farmers at the same time. And even if you ignore this connectivity issue, there is the issue of outages that I told you before. This connection is not reliable. You cannot rely on this connection for connecting to the cloud all the time because of weather-related outages that can happen. So what can we do? Well, our idea is to split the computation between the cloud and the local PC that sits on the farm. The PC can deliver all the time-sensitive applications locally and create summaries for the cloud. So I'll tell you in a bit what these summaries are, but they are 2 to 3 orders of magnitude smaller than raw data. Since the PC is providing these local services, even if a weather outage happens, it does not affect the farmer. And since these summaries are smaller, you can use this weak connection to ship them to the cloud whenever you want. And this cloud delivers long-term analytics and cross-farm analytics applications that cannot be delivered on-farm, but that are also not time-sensitive. Okay, so this completes the picture of the entire system. We have the sensors that are collecting data on the farm. They're sending it to the IoT base station, which talks over white spaces to this gateway PC that does most of the processing and provides local services to the farmer. And this PC also creates summaries that can be sent to the cloud for long-term analytics. So let's talk about a second challenge, which is the sparse deployment of sensors. So as I told you before, we would ideally want to deploy 1 sensor per square meter and get a fine-grained map of my field. And unfortunately, we can't do that because of physical constraints in the farm. So the question we want to ask is that how can we cover this large farm at a fine granularity with a small number of sensors? Our idea is to use drones. Drones are getting increasingly popular. They're also cheap. You can get a good DJI drone for $500 today. They're easy to program. They can quickly cover large areas. And they can collect visual data. They have cameras on them. You can just use them to collect visual data. So what we do is to combine the visual data that we collect from the drones and combine it with the sensor data for extending the spatial coverage. And let me tell you how we do that. So we take a drone, we send it across the farm to do an aerial survey of the field. We combine this aerial survey into a compressed overview of the field, which looks like this. This is the panoramic overview of the farm. And we compress this overview, combine it with the sensor data, and create a sensor map like this. This sensor map has the value of the sensor at each location of the field, even though we have a very small number of actual sensors deployed. Of course, to build this map, we need two steps. The first step is to go from drone video to the panoramic overview. And the second step is to combine this overview with the sensor data and get the sensor map. I'll not talk to you about the first part today. I'll focus on the second part, which is to combine this panoramic overview with the sensor data. So to do that, we formulate this as a machine learning problem, where the visual features of the field serve as inputs. And our job is to predict the sensor values. And the sensor data that we have actually deployed acts as the training data, and we want to predict it on the rest of the field. And to do that, we want to model two insights. One, we want to model spatial smoothness. So these are natural processes, right? They are smooth in space. So areas that are close to each other should have similar sensor values. And the second insight that we want to model is visual smoothness. That is, areas that look similar should have similar sensor values. So if you look at the top left of this graph, you can see that this part is clearly very wet. And that's exactly what we want to capture by this visual smoothness metric. To see how we do that mathematically, we use this machine learning tool called Gaussian processes. The nice thing about this tool is that you can use a really small number of sensors, less than 50, and you would still be able to get accurate measurements. So to model these insights, first we model the features as this variable xi. These are the visual features for each location of the field. And the output that we want to get is the sensor value, say moisture. So we know some of these YIs. We don't know a lot of these YIs because we have a sparse sensor deployment. And to model visual similarity, we have this kernel W. And for spatial smoothness, we model this kernel K. So we have modeled both of our insights into this model. And then at the training phase, we use the sensor data that we have to learn these parameters K and W. And once you have learned that, at the test phase, we can generate the precision map that I talked to you about. So what I've shown to you now is how we can use these drones together with the sensors to expand the coverage of these sensors. So one thing I want to note here is that this precision map is just 100 kilobytes in size, which is much smaller than gigabytes of raw data that we would have generated. And we can easily ship them to the cloud. So this is the unit that acts as summary for us. Cool. So now let's talk about the third problem, which is power availability. So as I told you before, power on the farm is really variable because of the weather. Solar power depends on weather, and sometimes it gets rainy, it gets cloudy, it's snowy, and weather goes bad, and these batteries would die down. So to understand this problem a bit more, what we did was that we put a solar-powered battery on the farm, and we connected a fixed load to it. And we checked the amount of downtime that this battery faced. And in some months which are cloudy, it could face as high as 30% downtime. That's huge. For 1/3 of my time, I do not have any data from the farm. And this data is important. This data is collected when it's raining, so you want to know how much rainfall happened in what part of my field. You also want to know what parts of my field were flooded and what parts were not. And you miss all of this data just because you have the solar-powered battery. So how can we deal with this weather-based power variability? Of course, we can't of course we can't control the weather, right? But what we can do instead is we can predict the weather. We can use these weather predictions to build a model that can predict my solar energy output. And based on that, I can save power for the future. So let's say I know that tomorrow is going to be cloudy. What I can do is start sampling my data less frequently today so that I save some battery for tomorrow. And that's exactly what we are going to do. To model this mathematically, let's say for each time cycle, we have our system on for T on and off for T off. And gamma is just the ratio between the two. And we want to model two constraints. First is power neutrality. which means that I don't want to consume more power that I can produce than what I produce. So let's say your system has a total power consumption of P, and your power budget is C. You want gamma P should be less than or equal to C. And the second constraint is specific to IoT systems, which is the minimum transfer time constraint. Every time you turn on, you at least want to connect to the sensors and collect their data. So your T on should be greater than or equal to T connect plus T transfer. And to solve these inequalities, you can plot them on a two-dimensional curve. There are two free variables, T off, which is on the x-axis, and gamma on the y-axis. And the first constraint can be plotted like this. This is the minimum transfer time constraint, which is T on is greater than or equal to something. And what you want is your set of parameters should be above this curve. And the second constraint is the power neutrality constraint that I told you about. And together they give us this feasible region. So you want your parameters to be anywhere in this feasible region. Which one do you pick? There's a lot of parameters there, right? So the idea is that if you look at the x-axis, as you move towards 0 on the x-axis, the latency of your system decreases. Your system is off for less amount of time. So we want to pick an optimal set of parameters that minimizes this latency. So what I've shown you is that we can use weather forecasts to duty cycle the system with the minimum latency. So this concludes the technical part of my talk. Of course, there's a lot more details, and I'd highly encourage you to read the paper for those. I want to quickly talk about our deployment. We've deployed our system for 6 months in 2 different farms. One was in upstate New York, and the other one was in Carnation. The farm in New York was larger with 100 acres, and the farm in Washington State was smaller, like 5 acres. We deployed 3 kinds of sensors, pH, moisture, and temperature, and we used DJI drones. And we also deployed a bunch of cameras for IR imagery on the farm, and also for monitoring storage areas. The cloud component was provided by Azure Storage and IoT Suite. So in all, we used like 10 different kinds of sensors from different companies, 3 different types of cameras, and 3 versions of drones. We deployed over 100 sensors in both these farms and about 10 cameras. And over the course of our deployment, we collected a lot of measurements. We collected like 10 million sensor measurements, 500,000 images, and we did over 100 drone surveys. So one of the most interesting aspects of our deployment was that in one of the weeks, the cloud connectivity broke down because of a thunderstorm. And the system was still functioning for the farmer. The farmer did not have any perceived delays, which is cool, right? That's what we wanted to do. From the perspective of a farmer, the farmer has to just program the drone flight once in a week or whenever he wants it. And then the drone goes over the field, collects the visual imagery. The sensor data gets combined with it and is sent over TV white spaces to the gateway. The gateway creates the panoramic overview of the field for the farmer to see, and the summaries for both the cloud and for the farmer. So this is how a typical panorama would look like. This is a 5-acre patch in the New York farm. This is a 5-acre patch. So if a farmer sees this, he can actually get a lot of details out of this. For example, there's a water puddle. This water puddle could render the field unusable for the next season. It's good that he gets informed about it just by looking at this. He can see cow excreta, which I'm told provides a good source of manure. He can also monitor his cows, and he can observe a stray cow. And this is another example of a panorama from the Carnation farm in Washington State. This is a smaller area, like 2 acres. And we can use this to generate the precision maps that I talked to you about. This is an example of a sensor map. It's a moisture sensor map. The scale is 1 to 5, and where 5 is more wet and 1 is really dry. So one really interesting thing to note about this is that this was generated using just 10 sensors on the field, and it has now like 4,000 measurements in this. The other interesting thing that I observed about this was that we did not have any sensor in this part of the field. And even then, we could figure out that there was a high moisture. That's because of a learning model. This is a pH map. pH is used to measure acidity. It's on the scale of 4 to 7 here, where 4 is really acidic and 7 is neutral. Typically, for most crops, you would want it to be between 6 and 7. And we could observe that this part was doing really bad. This is like more like 4. And we could inform the farmer that, yeah, you should probably take some action about that. To empirically evaluate its accuracy, we did another experiment. We went to different parts of the field, and we actually measured the ground truth sensor values using a sensor. And we compared it with the values that we had predicted. And I'm going to plot the mean error for 3 different kinds of sensors, where the temperature is in Fahrenheit, pH is from 0 to 14, and moisture is measured on the scale of 0 to 6. And these are our errors. So these errors are really small. If you look at the temperature error, for example, it's just 0.6 Fahrenheit, which is nothing. And to give you a perspective, I'm going to also plot the least count of our sensors. That is the granularity at which our sensors can measure the value. For example, my temperature sensor has the least count of 1. And what that means is that my temperature sensor can either measure 45 Fahrenheit or 46 Fahrenheit and nothing in between. So what you can see is that our predictions are doing comparable with the least count of the sensors. And what this means is that our predictions are as accurate as measuring with the sensor values themselves. So FarmBeats can accurately expand the coverage by using a sparse deployment of sensors and using a drone. So I'll quickly tell you about one more result about our paper, which is the weather-aware duty cycling component that I talked to you about. So this is a 3-day experiment. On the x-axis is the day, and on the y-axis is the cloud cover. As you can see, the first day is quite sunny, the second day is partially cloudy, and the third day is completely cloudy. So if you don't do any duty cycling at all, what would happen to your battery? So the x-axis on this other curve is the day, and the y-axis is the battery percentage. So as you can see, on the first day, when there is enough sun, the battery charges during the day and discharges during the night, which is an ideal behavior. That's what we want. But on the subsequent days, as you can see, the battery keeps discharging because there's cloud cover, and eventually it dies down. On the other hand, if you do FarmBeats-based duty cycling, that you predict the weather and you try to save for the future if you see cloudy days coming ahead, this is what you would get. So even on the cloudy days, you could still get some data, and your battery does not die because you had already taken that into account a priori. So we also did a long-term experiment with this mechanism, and we found out that the downtime that was 30% for a month could go down to 0 just because of FarmBeats-based weather-based duty cycling. Of course, all of our work is based on a large body of related work. There's been a lot of work in wireless sensor networks for agriculture and low-power, wide-area network technologies. But all of that work focuses on connecting sensors to each other. On the other hand, we build systems to take into account weak cloud connectivity, power availability, and we also work with a sparse deployment of sensors. There's also a lot of work in agriculture and ICTD communities on expanding precision agriculture, information access, and user interfaces. And all of that work is complementary to our work, and we believe that we can actually make that work reach the farmer and give him benefits. To conclude, I presented to you FarmBeats, which is the first end-to-end IoT system for environments constrained by the challenges that I talked to you about. We believe that it acts as a tool for the farmer to be more productive on the farm and to increase productivity of the farm. And it's actually being used by farmers for applications that we did not envision when we planned this tool. And on that note, a huge shout out to our farming partners, Sean Stratman and Martin Kusinkambil, and I'm ready for questions. Thank you.
Hi, Sanjay from Purdue.
Hi.
Nice talk. I never expected to see an NSDI talk begin with a slide that says why agriculture. But actually, my question is about some of the novelty of the work, right? For example, in the embedded systems community, there's been a lot of work on solar harvesting and so on. So can you perhaps talk about what are some of the novel nuggets compared to the work going on in those communities?
Sure. So there is there is the different components of novelty, right? For example, the combination of visual imagery with sparse sensor data, that's work that's not been done before. Even the solar power harvesting work, there's been a lot of work in actually Deepak's work and you using weather forecast to do it. But there are unique challenges that occur in agriculture and specifically for duty cycling a base station as opposed to a sensor. And those are the challenges that we tackle in the paper. And finally, there is the gateway design that splits this compute between the gateway and the cloud. That is novel. But on a more broad level, I think the novelty of the work is building an end-to-end system as opposed to focusing on unique individual components.
Okay, thanks.
Sure.
Hi, I'm Andrew Chi from the University of North Carolina. So it's really refreshing to see work that deals with some of the realities of an emerging economy, or so no internet, no power in many cases. So I'm curious, so I've spent the last 7 summers in South Africa, and one of the challenges there is how heterogeneous the environments are for farming. So it's the soils and just the environments. How easy is the training phase of your, like learning how to interpolate from a few sensors to the map?
So I think so. Is the question about the compute complexity, or is it about deployment scenarios?
It's more of a deployment question.
Okay.
Of my farm might be very different from one that's 10 miles or 10
Yeah.
kilometers away?
So we've validated across multiple farms. There's like
Okay.
the farm in Carnation, and then there's farm in New York, and there's multiple patches which are like completely heterogeneous. And we found out it to be consistently good. I hope
Okay.
like does that
So you
answer
can
the question?
train on your okay.
So yeah, there is no separate training phase.
Okay.
Training phase is not separated in time. It's actually separated in space. So there are some spatial values that you have sensor data for that acts as your training data, and for all the other values, you have to predict on them.
We can take that offline.
okay.
Sure, yeah, we'll take that offline.
Is
Yeah.
it a quick question? Yeah.
So good work, Deepak. A quick question is, when you fly the drone, you actually see the plant canopy, right?
Yes, we
And
do.
that's your visual data.
Yes.
But from that, you're modeling the soil moisture. So is there a latent variable where you look at the plant's leaf color and from that infer the soil moisture? Or
So there is two kinds of variations that occur. One is so there is the plant color based variation, and then there's also you could still see some soil, because if you fly low enough, you see the soil characteristics as well. So there is a difference in the plant cover, and as well as the difference in the soil characteristics themselves.
but your camera picks up the
Yeah.
variation between those two
Yeah.
because it
So
can be
it's-
totally plant covered.
So
right?
it's not explicitly modeled in the scenario, right? The system implicitly takes care of that.
All right.
Thanks.
Thank Deepak.